Welcome to the smartest decision you have ever made. Okay, now before getting into the video, what I'm trying to tell you is that I'm just going to tell you the summary of algorithms. Okay, summary of all the algorithms. I'm not going to tell you elaborate the algorithms. Okay, so let's get started. Now, the first algorithm we have, one of the most simplest algorithm in machine learning is KNN. Okay, KNN, K nearest neighbor. K nearest neighbor. Okay, now this is one of the most simplest algorithm and it makes prediction of new data by finding the closest data point. Okay, now what matters in the K nearest neighbor is two things. The number one is the number of neighbors that we are choosing and how the distance is getting measured. Okay, two things. Now the K in its name, okay, the K in its K nearest neighbor. Okay, the K in it is telling us the how many neighbors we need, which means K, which is a variable that is telling us that we can put as many numbers of neighbor we want, but there are only few numbers that is actually useful. Okay, that gives us a very sweet result. Okay, nearest neighbor. Okay, now K nearest neighbor. K nearest neighbor is good for like simple machine learning models. It is not a very production ready algorithm. Okay, and it is not recommended for large data set as we deal in the real life problem. It is good for project making and dealing with small data set, but in large data set, whether it is in features or samples. Okay, samples means the number of data, and features are how many features that we're using to predict the model. Okay, so it is not used. Okay, this is not even considered in using into the large data set because its prediction is very slow. Can be it's very slow. Why it can be slow? It is very slow because the distance is getting measured, and choosing a neighbor, that is very time consuming and computationally expensive. Okay, now it needs pre-processing, which means we have to deal with the data, we have to make the data in a way that can be predicted using the K nearest neighbor, and that is the thing that we have to take care of in it. And the K nearest neighbor is not actually used in practice that much due to its slow prediction. Okay, and its inability to handle many features. Okay, it cannot handle many features because if you have a lot of features, it will get confused because which data point to use. Okay, now we can see an example also here that we have two classes, 0 and 1, and we have two sets, one is training and one is testing. Okay, now in the red triangle, okay, the red triangle is training class 1 and class 0. Okay, now as we can see that we are have some these points here. Okay, these points, and what are these points? These points are test sets. Okay, these are the data of test set which is being predicted here. Okay, which is being predicted here by measuring the distance. Okay, and if we increase the number of neighbors, then it will use more neighbors to get predicted. Okay, now after seeing this problem that this algorithm cannot deal with many features, we move to the next algorithm, which is the most classic algorithm in whole machine learning journey, which is linear regression, which is the most popular and one of the most classical example of linear regression. Okay, now OLS, which is ordinary least squares, you would have seen in a lot of places that it is used. Okay, now we know how the prediction is made. We have a y, the prediction, we have weights, we have features, and it is being it gets multiplied and we get the our prediction. Okay, and for the prediction we minimize the error using the mean squared error, MSE. Okay, and the minimum the error, the better it for us. Okay, now suppose that we build a linear regression model. Okay, and we got a R2 score of 0.99%. Okay, 99% of R2 score. R2 score is the metric that we use to for the evaluation. Okay, now we got the 99% of to score. Now we thought that our model is so good that it predicts the 99% right. Okay, out of 100, 99 times our model will be good. Okay, but this is not the case, because the model could be overfitting and we don't know, and we are just chilling out and we are so happy that our model is so good that we can use in production. But it is not the case, because it is overfitting and we have to prevent the overfitting. Overfitting is a case in which what happens that the training the training set, okay, the training set is memorized or get into the or it is simple. What I'm trying to say is that the not this one, sorry, training uh, data set, okay, the training data set is memorized or learnt by the algorithm, so that it is giving us the prediction which is accurate, which should not be the case, because it should give us the error, because we are not something which is 100% accurate, okay, which is not 100% accurate. Okay, now this is the overfitting, and overfitting I have made a lecture of that also. You can go and see that. Okay, now we are dealing with regularization. We have to use a regularization. Okay, so regularization is a technique that is used to prevent the overfitting. Okay, and to prevent the overfitting, we use regularization, as we said. Now, for using regularization, we have some parameters in the algorithm that by using that we can reduce overfitting. Okay, we can reduce its overfitting. But in linear regression, we do not have any kind of such parameters so that we can control its overfitting scenario and its regularization. So there was an extension of linear regression was built. Okay, the ridge regression and the lasso regression. Okay, ridge regression and the lasso regression. So these both are the just extension of linear regression, but with some parameters that is used in the scenarios which they are capable of. Okay, the scenario where we need these two type of algorithms, we use them. Okay, now moving to the next algorithm, we have ridge regression. So ridge regression is a regularized model of linear regression, or the extension of linear regression. So it uses L2 regularization. Okay, in which what happens that all the coefficient are made as small as possible to close to zero. Okay, so what will happen is that, suppose this is our prediction, this is our parameter, and this is our feature, and this is with the whatever we say intercept. Okay, so this is made close to the zero, so it will have the less minimum to the minimum effect to the prediction, so that it cannot affect the prediction. Okay, so that is used to prevent the overfitting. Okay, and it has a regulation parameter which is alpha. Okay, and lower the alpha, greater the prediction or greater the generalization. Okay, so we have a code snippet here which shows us that changing in the alpha, okay, changing in the alpha drastically change the performance of the model. Okay, see, we have our ridge regression imported and being applied here, and we have alpha of 10. Okay, we use alpha equal to 10, which is a lot, and we have alpha 0.1. We can see as we have used 10. Okay, alpha equal to 10, we have training set of 0.79 and test score 0.64, which is a bad model. Okay, but as we can see, we have the alpha close to 0.01. Okay, the very lower alpha, and our generalization and or prediction of the model has been increased. Okay, has increased drastically. So does we mean that the lowest the alpha, better the performance? No, lowest the alpha can actually affect the model by not getting the prediction, because the highest, not always the time the streams are good. Okay, that is thing. So we have to find a sweet spot where we can get the good generalization of the model. Okay, we can see that we have improved from 79 to 93 and 64 to 77. We have improved drastically. So this is the thing, and we have a graph also which shows us how in the number of samples can affect the model. Okay, we can see that we have two models, the linear regression and the ridge regression, and we have two sets, the test and the training sets. Okay, now we can see that the training set size, the number of training size we have, and the R2 score, the R2 score here, which is the evaluation metric, so that we can check the generalization of the model, how good it is. Okay, so we can see that the ridge regression performs very bad on very minimum data sets. Okay, like 100, 200, 300. It performs like I would say average, because it is between 60-70% of score, but the test is like good. Okay, it is good but not that good. But as we can see, as the number of sample or number of training size increasing, okay, increasing, and when it comes to close to 400, we see the drastic change in linear regression, that it gives us score of around 75. Okay, I'm not that accurate, but we get 75, precisely 75% of R2 score. Okay, and the test set score is also greater than the ridge regression. Okay, so what we got is that number of samples matters a lot for the training of the model. Okay, now moving at the equation that we use to for the ridge regression, which is alpha, that we used here, which controls the regularization. Okay, not the regularization, but which is a regularization technique to control the complexity of the model, that how well it will generalize. And then we have our weight squared. Okay, weight squared, this is the equation that is used. Okay, in the penalty, in the mean squared error. Okay, now we have alternative, which is L1 Lasso regression, which is L1 regularized model. So what it does is that it makes some coefficient exactly to 0. Okay, exactly to 0. Okay, then we have its regularization parameter alpha, and the equation that is used here is this, the alpha that we have used here, and the W. Okay, WV means weight or the parameter. Okay, or the slope, whatever you say, the absolute value of W of weight and the alpha. Okay, so what L2 and L1 regularization are? Okay, L1 and L2 regularization. Okay, so L1 regularization, when we need only few features. Okay, only when few features are important, we use L1 regularization, and when we have to use every features but with the minimum effect, we use L2 regularization. Okay, every feature but minimum effect. Okay, minimum effect, that is the thing. One more thing is that large number of feature. Okay, large number of feature are very important in the linear models. Okay, but before that, we have another model, which is elastic net. Okay, which is elastic net, which uses the both L1 and L2 regularization. So if we need both, we need combination of both, that we have to use the minimum feature. We have to use very few feature, and we have to have its very minimum effect. Then we can use elastic net. Okay, and you can go and read the docs on sklearn. That is a very good resources, and you can go and you can learn more about them. Okay, so what I was trying to say is that in the linear model, the number of feature or number of data or samples are very important. They play a very crucial role in the prediction of the model. Okay, Now moving ahead, logistic regression. Now logistic regression is another linear model, but it is used in prediction of classification problem. Okay, classification based problems. Now in logistic regression, we do the same equation that we have done for the linear regression, but we have a threshold, and the prediction above than the threshold belongs to some class A, and the prediction below the threshold we classify to class some, okay, some another class, okay, A or B, whatever. Now most commonly okay, so the most commonly used linear classification models are logistic regression and linear SVC, which is linear support vector classifier. Okay, now the regularization parameter here is C. Okay, now C means nothing, just it is C. Okay, now higher the C, lower the regularization, and lower the C, higher the regularization. Okay, by default it uses the L2 regularization, and I have told you what L2 regularization does. Okay, now we have a code here, we have some code snippets which is telling us that for which value of C we get the best result. Okay, so we have used our training accuracy. Okay, the accuracy, we have used the accuracy parameter to evaluation metric to check the performance. Now for the training, using the 0.01 we get 0.91 and 92. Okay, and for 1 we get 96 and 96. Okay, and for 100 we get 99 and 98. Okay, we get 99 and 98. Now so as we get 99 and 98, why just not, yeah, as we are getting 9.9 99%, 98%, we can confirmly say that this is overfitting. This is overfitting because we cannot achieve this number. We can never achieve this number. There should be error. There should be error because errors are actually good, that we can say that our model has made prediction, because a prediction always has some error. It always gives error. Okay, now we can say that the sweet spot here is C equal to 1, because it gives us a very reasonable 96 and 96 for test and a training and testing set, 96%, which is a very good number. And we have also got 91 and 92% by using 0.01. Okay, 0.01. So we can choose which to use based on some conditions and on the data and on the prediction on the classes. Okay, so that is the thing. Okay, now we can actually say how the prediction is made, how we have made the prediction by using the graph. Okay, you can see here also using the code we done, that it predicted very well, it also predicted very well. So now what has been done here, this is the most sweet spot between among these three, because if something lies here it belongs to this class, if something lies here this belongs to this class. But here we have very very stricted boundary, so that whatever comes here, even it belongs to this class, will belong to this class, and if something belongs to this class comes here, it will belong to this class. So yeah, we have to find the sweet spot also, not extreme. Okay, not extreme numbers are always better. We have to look for the sweet spots. Okay, now the next algorithm is naive Bayes. Okay, so naive Bayes are very fast to train, they are very fast trained, but they have worse performance than the linear as we see in linear logistic regression. And naive Bayes is a classification based algorithm. Okay, classification based algorithm. Now in naive Bayes we have three types of naive Bayes: Gaussian naive Bayes, Bernoulli naive Bayes, and multinomial naive Bayes. So Gaussian naive is used for continuous data, Bernoulli naive is used for binary data, and multinomial used for quant data. Okay, now these two, Bernoulli and multinomial, used for text classification also, okay. Now if we talk about the use of Bernoulli, so Bernoulli classified count how often every features of each class is not zero. So what it does is that we have set of features here and we have its class associated to it, okay, the actual class set, and it will check that for each class which has non-zero most of the time, okay, non-zero. So if we say this, for the first 0 we have 2 1 and 2 0, okay. For second one we have 3 1 and 1 0, and for this third we have 1 and 3 0, and as on. So the more one, okay, more one, the better for it, okay. The number of one more, okay, more than number one, it is better for this, okay. Now multinomial, so multinomial and Gaussian, so they use some statistic technique and computation for their modeling and their training, okay. So multinomial NB use the average value of each feature for each class, okay, average value of each feature for each class. So it uses its average value, it uses this average value and this average value. Now Gaussian base, okay, it uses the average value with its standard deviation. For multinomial and Bernoulli naive Bayes, we have the parameter alpha, which is the regulation parameter for controlling the complexity of the model. Okay. Now moving ahead, the Gaussian naive Bayes, this is used for very high dimensional data. Okay. And multinomial is actually chosen than Bernoulli for the large number of data which has non-zero features, okay, non-zero feature, which means 1, okay. Now naives are very fast to train, and they predict very fast, but their training procedure is also very easy, okay, but they are not used that oftenly, okay, because they are not good with that very large data set, okay, and they give very worse performance, okay, that is the thing. Now moving ahead, we have decision trees, and we know how decision tree is training is done. It asks some questions, and then whether it's no or yes, it's divide, okay, it gets divided and divided till it gets its last query, okay. Now as we can see that name suggests decision trees, we have a tree, okay, and we have its branches, we have its branches. Now each of these, this is not good for us, okay, so we get 100% of accuracy, which is not good for the model, okay, which is overfitting, and we have to prevent the overfitting, and for prevention we have two things: pre-pruning and post-pruning, which is also known as pruning, okay. So pre-pruning, what it does is that it stop the growth of tree before the pure, okay, before the pure, and we use max depth for the its prevention, okay. So now what is depth is, this is depth 1, this is depth 2, this is depth 3, till it reaches the pure, because if we set the number of depths, okay, we can have more questions, okay, more questions and more questions. So if we set the number of depth, okay, we number the depth, then we cannot reach to the its pure. Yeah, so the ways in which we can prevent the overfitting and decision trees are two ways: pre-pruning and post-pruning, or we can say that pruning, okay. So in pre-pruning, what is that it does is that it stops the growing tree before pure, okay, using the max depth. So max depth is a parameter in the decision tree class in the sklearn. So we can set the max depth, and it can reduce the overfitting, okay. So it is a regularization parameter that controls the overfitting of the decision tree, okay. And then we have post pruning, and the post pruning, what we do is that we remove the leaf after building the tree, okay. So we remove most of the tree after building it, okay. Now we are moving to the another part, which is the feature importance in the decision tree. So in decision tree, there are a lot of features which are important to the decision, because for making a decision we have to get through the question which is important for making some decisions. So we have to get the importance of the feature to get the which feature is important, which features is not. Okay, now we have some parameters which can control the complexity of the decision tree, which is max depth, max leaf nodes, and min samples leaf. You can go on the sklearn.org, sklearn.org, okay, org, and you can know everything about it. Okay, you can read the docs of it. Okay, docs of it. Okay, so the one of the few benefits of decision tree is that it is very easy to explain. Okay, even if it's some 4 or 5 year, not 4 or 5, but a kid in 10th or 9th or in high school can be made understand, can made be understood about decision tree. Okay, and we need no pre-processing for it. We do not need any kind of scaling like standard scaling and min max scaling or any kind of scaling and pre-processing for the data. It just gets just make the prediction very well. Okay, and one of the like disadvantage of decision trees that they overfit. They are overfit. Okay, now, due to overfitting of decision tree, we got another idea and we made another algorithm, not me, but the experts, called as random forest. Okay. Now, this is an ensemble method. Okay. And what ensemble method is that? Ensemble method is combining multiple machine learning models to create new, more powerful models. Okay. So, what it does is that decision tree uh, is made to new random forest. Okay. Now, due to decision tree overfitting, we made a random forest, and as its name, okay, random and forest. So forest where we have a lot of trees, which means a lot of decision trees, and random means randomly trees. Okay, so we'll get it. So random forest is called random forest because it has randomness in its tree. Okay, it uses bootstrap sample to uh, with it uses bootstrap sampling. Okay, or bootstrap sample. So what it does, that we have a original data set A, B, C, D, and what it does that for each tree, okay, the number of trees we will assign, for each tree it gives different data set. Okay, different data set. So this is the original A, and for the B tree it gives A, D, D, C, and for C it gives D, A, D, A. Okay, and that's how it works. Now we have different trees and each tree predicts. Okay, and the parameters is n estimated the number of trees that we want and max feature number of features. Okay, how many features are important. Okay, and the feature that will assign will be assigned randomly to the each tree. Okay, suppose we have this tree and this tree, it will have a feature, it will have this feature, it will have this feature. Okay, and then we have another tree in the forest. Okay, so we have this tree, then we have another tree. Okay, another tree, then we have another tree. Okay, then we have another tree, and this is how random forests work. We have lot of trees, the number of trees we assigned by n estimated, and the max feature that we want to, that how many features that we want to use. Okay, now they're very powerful. Okay, they're very powerful, and if I tell you a story, then what happened is that my machine, okay, my MacBook, I'm building a project. Okay, and I used random forest in it, and literally, man, it went to 100 degrees Celsius. It went to 100 degrees Celsius and 100% load on the CPU. 100% load in the CPU, because I used all my cores on this process to use all the power of my uh, machine to predict, and it literally scared me because I do not want any of my CPU or any of my connection between them to get blown up. I know, but I know it won't, but I do not want to get in risk. Okay, so I used cloud. Okay, so I used cloud or any another platform which I can perform these very powerful models. Okay, so yeah, it, as we know that trees do not need any kind of scaling, And a very important feature we have n jobs. So n jobs is a feature in which we can assign how many cores do we want to get involved in this training set. Okay, so if we set, suppose you have 8 cores and you give it 6, so what it will do is that it will use your 6 cores. Okay, sorry, it will use your 6 cores, all 6 cores, to uh, predict for the model to predict. Okay, and if you use -1, which means it will use the whole core, okay, the whole set of core to predict. Okay, that is the thing. So don't be smart and use minimum core, because if you use minimum core then it will take very long to compute, because these are very powerful. There is a lot of number of trees, so it is very computationally expensive. And if you use all your cores, then definitely be ready to get blown up and get fired in your computer, because it is very powerful and it takes a lot of computational power. So it won't happen, but still I'm saying it. Now the very disadvantage that they are very trained to slow, and very slower to train and predict than linear model. Okay, so it has a lot of things to do behind it, so it needs time to compute, so it is very slow, it is very slow. Okay, now uh, it has some parameters like n estimator, max feature, max depth, which controls the complexity of the model, and max feature tells how random the forest is, and lower the max feature, lower the overfitting. Okay, this is how it works. And max depth we have actually know it. Okay, you should be knowing about this. Okay, now gradient descent is another step of it. So gradient boosted trees. Okay, so these are also ensemble method, and it uses the decision trees, but it uses another technique. So what it does, that is use strong pre-pruning. Okay, and if we do not get into that term, that so let me tell you. So what it does, it builds a decision tree, and whatever it mistakes is that it has done, it is corrected by this decision tree. Okay, so whatever mistakes this decision tree has done, this won't, and whatever mistakes this decision tree has done, the next won't. Okay, this is how it works. Okay, now let's talk about the thing that I've written. So it uses strong pre-pruning, small shallow trees of that 1 to 5, so it don't use a very max depth of trees. It uses 1 to 5 depth only. Okay, and but a lot of decision trees. Okay, so smaller in memory and faster in prediction, so it takes smaller memory but faster prediction. So the main idea here is that combine many simple models, like which is called weak learner. Okay, and more trees are added to it iteratively. Okay, so we have to make very small models but a lot of models. Okay, there are a lot of models now. Okay, so now gradient boosted trees are the most used and most winning model in the industry. Okay, like gradient boosting, ADA boost, and XGBoost. And XGBoost is the number one model that is used in the whole industry. Okay, this is the model that is used to make the prediction. This is the like father of all the models. This is the best model. Okay, okay, and we have learning rate in it for the controlling the regulation parameter. The regulation parameter is learning rate, how strongly each tree tries to correct the previous tree. Okay, as I've told that how much correction do we want from the previous tree, okay, to the next tree. If this had made a lot of mistake, then we have to take care of a lot or less. Okay, this is the thing. Now these are the most powerful models. We need careful tuning of parameters, because they take a very long time to train. We do not need any kind of scaling, and they work for both classification and regression based problem. And they are not actually good on the high dimensional sparse data, which means if they have lot of zero in it, then it is not a good model. Okay, moving ahead, uh, we have n estimators. Okay, depending on the time and the memory budget, because see, gradient boosted trees are like very huge, so we need how much memory we have and how much time we have. Okay, because they are very computationally expensive. Okay, that it. So these are the parameters we have to take in consider to while using the gradient boosted trees. The one is an estimator, second is learning rate and max depth. Okay, got it. And depth, number of trees, and learning rate, how well we want to prevent the mistake done by the previous one, and max depth, that how depth, uh, how much depth we want. So low is good. Okay, like between 1 to 5 are good. Now moving ahead, SVM support vector machines, that are very good. Now, what the support vector machine does is that we have data set and uses supports. Okay, it uses support terms of vectors, and it makes a line between them, and something that lies here are considered as class, whatever class we want to say, class A, and here class B. Okay, now in SVM, they are for the high dimensional data set, they are very computationally expensive. So we use kernel trick. Okay, kernel trick, the equation here we have the equation we have. Okay, which is equivalent distance. This I'm not going to explain what this equation does, but this is the equation for the kernel trick. Okay, so what kernel trick actually does is that when we have high dimensional data, they are very computationally expensive. So to reduce the computational expenses, we use kernel trick. Okay, we use the kernel, and as we also call as the kernel trick, to uh, lower the computationally expensive. Okay, now there are lot of kernels. Okay, there are different types of kernels like RBF. Okay, that we're going to talk most here. So the kernel RBF we have, and the parameters we have are gamma. Okay, C regulation parameter are the two parameters that are used for tuning the model, and smaller gamma means larger radius for Gaussian kernel. We are going to talk about it, and it needs pre-processing and scaling of min-max scalar. Okay, or whatever scaling according to the data. Okay, now SVM. Okay, for SVM we need careful pre-processing. Okay, we need to tune its parameter C. Okay, and the kernel RBF. Okay, and they are, and if we have lower, okay, less samples, okay, then it is good. But if we have higher samples, it has very high runtime and high memory usage. Okay, that is the thing. Now let's get into this thing. Okay, the summary of it, the summary of our whole model. Okay, for nearest neighbor, it is good for small data, good as a baseline project, which is very easy to explain. Okay, now for linear model, it is go to as a first algorithm to try, good for very large data, good for very high dimensional data. Okay, as we talked, naive Bayes only for classification, even faster than linear model, good for very large data and high dimensional data, often less accurate than linear models. Okay, decision trees very fast, we do not need any kind of scaling, can be visualized and easily explained. Okay, random forest nearly always perform better than single decision trees. Okay, because in random forest we use many decision trees at one place. They are very robust and powerful, we do not need a scaling, not good for very high dimensional sparse data which contains 0. Okay, sparse data are the data which contain 0. Now gradient boost and decision trees, more accurate than random forest, like, and slower to train because there are a lot of things going behind it, and it is very slow to predict than random forest, and smaller in memory, they take very less memory, but they need more parameter tuning than the random forest. Again, now support vector machine powerful for medium sized data set of features. Okay, with similar meaning, require scaling and sensitive to the parameters. Okay, so that is it.